Okay, move on to vertical stress caused by a vertical strip load. We are referring to finite width and infinite length. So this is an illustration for a vertical strip load that it may cause on vertical stress at certain point. So the point that we're talking about is this one. What will be the stress at point A due to this vertical strip load? So you have a uniform loading. So the equation for stress from a line load will be because to find the stress due to a strip load of width B is given by this expression. So we simply have to identify our parameters on our equation. So upon integration, our stress caused by this vertical strip load is equal now to this expression. So we just have to identify, of course, our intensity and the magnitude of our vertical strip load, the Z, which is the distance from the strip load towards the point of the stress caused by the strip load, our B, which is the width of the strip load. And we have to take note that this equation, we have to bear in mind that all of this are in radian, and the magnitude of this magnitude that we have computed should be the same as the value of x all over z and in the table. So this equation is valid when this equation is valid for a point, for a certain point or a point A when x is greater than or equal to b all over 2. However, if x is 0 or x is less than b all over 2, this magnitude will be replaced by this expression. So we have here the variation of delta sigma sub z with respect to q with different values for 2z all over b and 2x all over b. So we just need the value for 2z all over b and 2x all over b so that we can have the value for the stress delta sub sigma sub z all over q. So this also a representation of the variation of delta sigma sub z with respect to q with different values for z all over b and x all over b. So we have here a sample problem. Refer to the figure given we are having b is equal to 4 meters, q is 100 kilonewton per meter squared. At point A, z is equal to 1 and x is equal to 1. Determine the stress at point A. So basically, the figure that you are referring to is this figure for that particular sample problem. You're given with the parameters present on our equation, and we're going to solve for the stress caused by the vertical strip load. So we have to identify that our x is given, which is equal to 1 meters, and if you're going to get the value for b all over 2, it is 2 meters. So x is less than b all over 2. So we need to say our equation, this one, we have replaced, based on our rule, we have to replace the second part on our equation. So we have replaced that by this one. So this is now our equation to compute for the stress caused by the vertical strip load, since our x is less than b all over 2. So we need to get the value for each. So for this one, we simply get the value for the first. For this one, we get the value for this, we get the value for that. It was simplified, so we have here the values of 0.0785 rad, 0.322 rad, and negative 0.8. So we try to substitute that onto our equation. So it gives us this equation, which is 0.902. So we need to say this one was simply substituted to this one. We get this value, we get this value, we get this value, and we try to simplify and substitute. We have now this value, delta sigma sub C all over Q is equal to 0.902. So if we try to compare this one to our table 10.4, having the value 2x all over b, which is 0.5, and 2c all over b, which is 0.5, based on our table 10.4, our delta sigma sub c all over q is 0.902. So basically, our 0.092, we try to, from this equation, delta sigma of z all over q, which is equal to 0.902, we try to multiply this one, where q is 100, so you can now get your stress caused by the vertical slip load, which is 90.2 kilonewton per meter squared. So we move on now to linearly increasing vertical loading on an infinite strip. So for this one, what will be the stress at point A due to this triangular loading? So we have here the equation that you're going to use. You have q all over 2 pi, quantity 2x all over b, alpha minus sine 2 delta. So this is the stress caused by this triangular loading. So we have here a table 10.5, the variation of delta sigma sub c all over q with having a value of 2x all over b and 2z all over b. So we just need the value of 2x all over b and 2z all over b so that you can get the value of delta sigma sub c all over q from this table 10.5. So we have here a sample problem. Refer to the figure 10.18 for a linearly increasing vertical loading on an infinite strip. We're given with B, which is equal to 2 meters. Q is 100 kilonewton per meter squared. Determine the vertical stress at A, which is -1 meters and 1.5 meters. So for that one, we're given with this figure. So for this figure, we have to identify, we're given with, this is point A. Point A, from this point, this is our triangular loading. So what would be the stress caused of this triangular loading to point A? So what would be the stress of point A due to this triangular loading? So of course, this is, we have our quadrant, we have our Cartesian coordinate. So from point A towards this point is denoted as -1 meters. From this point towards point A is 1.5 meters. From this point towards this one is 2 meters. So we simply have to get our alpha 1 and alpha 2. We can get our alpha. So if we're going to get alpha 1, so we have here alpha 1, of course, is tangent of, actually this is arctan of 1.5 all over 3. Alpha 1 is this one, this alpha 1. So simply have to, we have 1.5, our z is 1.5, since alpha 1 is towards this point, so we consider this triangle, so that would be alpha 1 would be arctan of 1.5, this is y all over our x, so 1.5 all over 3, and it gives us 26.57 degrees. For alpha 2, this is our alpha 2, that's 1. So we consider this triangle for alpha 2, so that would be y is 1.5. So arctan of 1.5 all over 1, which is now 56.3 degrees. So okay, once we have alpha 1 and alpha 2, we can get our alpha. We simply have to subtract 56.3 degrees subtracted by 26.57, it gives us 29.73 degrees. So this is now our alpha. So 56 minus this one is 29.73 degrees. Now you can get your alpha 3, which is alpha 3 would be equal to, of course, this one from this figure, this alpha 3, this one would be 90 minus 56.3, because we are trying to get this is 90 degrees. This one is 90 degrees, so that would be 90 degrees minus alpha 2 would give alpha 3. So that is 33.7 degrees. Now you can get your delta. That is negative alpha 3 plus alpha. So it gives us negative 63.43 degrees. And of course, 2 delta is negative 126.86 degrees. So basically, from our figure, or from our equation, from this equation that was presented a while ago, you simply have to get the substitute. You can substitute our parameters, alpha, small delta, and this ratio is equal to 0.0447. And if you try to compare this one to table 10.5, we have here 2x all over b is negative 1 and 2z all over b is 1.5, and the value to that is 0.0047. Then from this equation, delta sigma sub z all over q, which is 0.047, multiply this one, first multiply, so you multiply by q. Our q is 100, so now the stress caused by the triangular loading is 4.47 kilonewton per meter squared. Now we move on to the vertical stress caused due to embankment loading. So this is an illustration for an embankment loading. So you have here an embankment. This is an embankment. So basically, this is the stress that you're going to compute. What will be the stress at this point at a certain distance z along y direction from the embankment. So of course the embankment has a height of h. So from this point, this is b1. From this point towards this point, that is b2. So to compute for the stress due to embankment loading, you have this equation. So this is the equation for the stress caused by the embankment loading. So basically, we're going to have the unit weight times h over our all over pi times b1 plus b2 all over b2 times alpha 1 plus alpha 2. So minus b1 all over b2 multiplied to alpha 2. So for that, our sigma sub O is, of course, that is gamma times h, the unit weight of the embankment of the soil and the height of the embankment. Our alpha 1, which is in radian, so we have this equation, and alpha 2, we are given with this equation. So we can simplify our stress due to embankment loading by this equation, Q sub O times I sub 2. Wherein our I sub 2 is a function, of course Q sub O is this one. Our I sub 2 is a function of B1 over Z and B2 over C. So we just need to get the value of B1 all over C and B2 all over C so that we can get the value of I sub 2 in figure 10.20. So that's one. We get the value of B2 all over C, B1 all over C from this figure. So whatever is the value of B1 over C, draw a line upward as it intersects to the value of B1 all over C. We draw a line horizontal so that we can get the value for I sub 2. So